This is Nikola Tesla, the greatest inventor of all time, and this is his greatest invention, the AC induction motor. In the early 21st century, modern inventors like Elon Musk started putting these AC induction motors into electric cars. From this, Tesla Motors was born. Elon Musk's Tesla has been constantly improving on that century-old design, from their Model S to the Model 3 and onto their next-generation electric car that has yet to even be released. This is how Tesla reinvented the electric motor. The AC induction motor is a product that goes back to the early days of Tesla Motors and the development of their first roadster vehicle. But in the grand scheme of things, the induction motor actually tracks its origin back to the early days of the Industrial Revolution. Alternating current is the kind of electricity that surrounds us on a daily basis. It's what comes out of the sockets in your wall and moves through the power lines up and down your street. Nikola Tesla is widely considered to be the father of alternating current electricity and was a pivotal figure in adopting AC to power the US electrical grid around the turn of the 20th century. Many people consider Tesla's greatest invention to be the alternating current induction motor, essentially a device that will transform AC electricity into mechanical motion, and in turn, when used in the opposite direction, an induction motor can turn motion into electricity. One of the first large-scale applications of Tesla's AC generator was capturing hydroelectricity at Niagara Falls. When we say alternating current, we are really talking about the direction that electricity is moving through a circuit. So, for AC electricity to work, the direction of the electric current has to continuously alternate between forwards and backwards. This is a bit difficult to imagine in the context of our own electrical grid. As far as we can tell, electricity flows out of the generating station and into our house, but in reality, it's in a constant state of movement back and forth. This is a characteristic that allows AC electricity to be transmitted at high voltages over very long distances and then converted into lower voltage for final delivery to the consumer. The alternating flow happens so fast that we only perceive the electricity as constant, but in reality, the direction of electricity alternates 60 times per second in North America. So how does this apply to electric motors? Well, it's all about magnets. So when you transmit electricity through a conductive material like a copper wire, you also create a magnetic field in that wire. This is an electromagnet, and once you stop the flow of electricity, the magnetic field will also dissipate. Now, if you transfer electricity in one direction through a conductor, you create a magnetic pole, either a south pole or a north pole. And then if you were to reverse the flow of electricity through that same conductor, you would also reverse the polarity of the magnetic field, so as the direction of electricity alternates, so does the north and south pole of the electromagnet. There are two essential components of an electric motor, the stator and the rotor. The rotor rotates and the stator remains stationary. Easy way to remember which is which. Now, as the name suggests, an induction motor uses a rotating magnetic field in the stator to induce a rotational force in the rotor. Here is how that breaks down. Your stator is essentially a ring of copper wire that is arranged into coils that run from the front to the back of the motor. Each coil of wire is wrapped around a piece of iron, so when electricity is flowed through the coil of wire, it becomes a powerful electromagnet. The polarity of each magnet is determined by the direction of current. So by alternating the directions of the electrical charge being applied to each subsequent winding and flipping each polarity in sequence, we create a rotating magnetic field that travels around the ring of the stator. The speed at which the magnetic field rotates can then be controlled by the rate at which you can alternate the flow of electricity. The rotor in this case is a much more simple component. There are various different kinds of rotors used in different induction motor designs, but the one that we are going to focus on today is known as the squirrel cage rotor. It gets the name because the structure is a cylinder made from aluminum bars that run from the front to the back of the rotor with circular metal end caps. There is no supply of electricity flowing into the rotor, and it contains no natural magnets. It's literally just a metal cage that can freely rotate, and yet the rotor can be transformed into a magnet by the rotating magnetic field of the stator. One of the interesting things about magnets is that they move relative to a conductive material. They can induce an electrical current into that conductor, which in turn creates an electromagnet with no contact required, just relative motion. You can see this by dropping a magnet straight down a copper pipe. As the magnet falls, it will induce a magnetic field into the pipe, which will then work against the magnet itself and slow the fall of the magnet through the tube. So the further it falls, the slower it will move through the air due to resistance from the induced magnetic field in the copper pipe. The same thing is happening inside the induction motor. By rotating the magnetic field around the stator using alternating current and electromagnets, a magnetic field will be induced in the bars of the squirrel cage rotor. That induced magnetic field will react against the magnetism of the stator. We know that magnets with the same polarity will push against each other, and this force of magnetism will cause the rotor to turn in the direction of the stator's magnetic field. So the faster you alternate the flow of current through the stator, the faster the rotation of the magnetic field, and the faster the movement of the rotor due to the magnetic push effect. The only caveat we need to remember is that the rotor will have to move at a slower rate than the rotating field of the stator, because the magnetic field is created by relative motion. If the two are turning in sync, then there's no longer any of that motion in play. The rotor will demagnetize and slow down. From the time this induction motor was first patented by Nikola Tesla, 1888, to the present day, AC motors have been a staple of industrial society. We see them in everything from elevators and streetcars to ceiling fans and washing machines. Anything that plugs into the electrical grid and spins is more than likely to have an AC induction motor inside. So when it came time for Elon Musk and his crew of founders at Tesla Motors to choose a power source for their first electric roadster vehicle, there was one very obvious candidate: the AC induction motor. And when used in an electric vehicle, the design gives you one significant advantage. We know that when you rotate the magnets of the stator faster than the rotor, you electrify the rotor and create a magnet. But when you spin the rotor faster than the stator using an external force like a wheel, you electrify the stator, which can then transfer the excess energy back to the battery pack and increase the driving range of your vehicle. This is how regenerative braking works. Tesla retained the AC induction motor as their primary drive unit into the Model S and X. This allowed the relatively large and heavy vehicles to achieve mind-boggling feats of acceleration from a standing start, but they also came with a significant drawback that needed to be solved. So the beauty of the AC induction motor is its simplicity. Coils of copper wire, some chunks of steel and iron, a squirrel cage of aluminum bars, not much to it. And that's exactly why the motors in appliances like air conditioners and washing machines can run for decades without failure. The downsides of the original induction motor start to show themselves only when you go in search of maximum power and efficiency, which is exactly what Tesla was looking for when they designed their Model 3. Okay, so everything that we just talked about still applies to this new motor that Tesla created for their Model 3, but with one key addition: permanent magnets. Specifically, they added permanent magnets to the rotor, so now instead of an aluminum squirrel cage, we have this dense iron core filled with strips of a magnetic rare earth element called neodymium. The technical name for this new motor type is IPM-SYN-RM. That means internal permanent magnet synchronous reluctance motor. It's complicated. Here's the scoop. You could make a permanent magnet motor by taking a metal cylinder, sticking 4 magnets to the outside with south poles on the top and bottom and north poles on the sides. That would be your rotor. And then when you stick that inside the stator that we talked about before and start rotating the electromagnetic field in the stator coils, your permanent magnet rotor will follow. Now, we can actually spin the rotor at the exact same speed as the rotating magnetic field of the stator, because we are no longer relying on relative motion to induce the magnetism in the rotor. This already gives us higher efficiency and more power, particularly when accelerating from a stop, because we have these two very powerful magnetic fields that can instantly push off from each other. But there's a big problem. 2 problems, really. For one, permanent magnets stuck to the outside of the rotor will have a tendency to come unstuck due to centrifugal force, so the faster the rotor spins, the more likely it is to fly apart. But even more importantly, reason 2, is that the rotation of the permanent magnets will start to induce their own magnetic field into the stator coils at high speed, and this is going to be opposite to the electromagnetic flow in the stator, and that force is going to want to slow down the whole system. This is called back EMF, and the faster the rotor speed, the more back EMF you get. To combat these two downsides, we introduced the design of a reluctance motor. So aluminum and copper are only magnetic when you flow electricity through them, but iron is naturally attracted to magnetic fields. So that means we can use it as a rotor material inside our same old electromagnet stator, and that iron rotor will follow in sync with the rotation of the stator's magnetic field. Again, there is one caveat. We need to cut channels into the iron material that line up with the shape of the magnetic field that surrounds it. This will align the magnetic reluctance of the iron core with the magnetic field of the stator and allow them to rotate in sync. This is our synchronous reluctance motor. It's a very efficient motor design, and it works very well at high speed because there is no back EMF created by the iron rotor. The downside here is that a reluctance motor has very low power density when accelerating at low speed because the rotor can only follow the rotating magnetic field of the stator. You don't get that instant push effect of two magnetic fields working against each other. Now, all we need to do is add magnets to the rotor and we get our perfect combination. Those channels that we cut into the iron core make the ideal location for our permanent magnets to live. This is our internal permanent magnet. By placing them inside the iron rotor, we reduce the permanent magnet's effect on the stator windings and thereby reduce the problem of back EMF. Now, there is still a very complex task here that involves balancing the reluctance effect of the iron core with the magnetic push of the permanent magnets. You see, you want to utilize the power of permanent magnets during acceleration, but then cancel them out and switch over the efficiency of reluctance at cruising speed. This is all handled by very advanced software controlling the magnetic field of the stator that we cannot even begin to explain. And this is why the IPM Syn RM motor was never widely used until Tesla came along. And now Tesla is about to take this design to the next level. With the motor design for the Model 3, Tesla was able to maximize both power and efficiency, but it did come at a cost. If we remember back to the original induction motor, it came with a relatively simple and cheap rotor made of aluminum bars. By switching to IPM Syn RM, Tesla introduced the rare earth element neodymium into their rotor, so the cost in this instance is money. It's a much more expensive motor. Now Tesla is dedicating their research and development into a next-generation vehicle platform that is supposed to dramatically reduce cost while maximizing efficiency. This will serve as the base for their upcoming robotaxi vehicle. From what we learned last year at Tesla's Investor Day, the designers are achieving much of that cost reduction by eliminating rare earth elements from the motor's composition. Now, it's not that neodymium is particularly scarce in the overall composition of the Earth, but it is difficult to locate near the surface, and you typically won't find large concentrations all in one place, so therefore the cost is relatively high, and the supply is relatively low. But engineers still prefer neodymium for electric motors because it has a strong magnetic field that won't degrade over long periods of use, so it does justify the cost. Now, Tesla is saying that they can get by without the need for any rare earth elements in their new magnets, so what will they use instead? A widely popular material for making magnets is called ferrite. This is a ceramic material of mostly iron oxide, also known as rust, combined with additional metals like manganese, nickel, and zinc, but it doesn't particularly matter which one. You'd find ceramic ferrite magnets in everything from speakers to electric guitars and cordless drills. They also help keep your refrigerator door closed, so it's a very common and affordable material. The downside of ferrite compared to neodymium is magnetic strength. You would need a much larger quantity of ferrite to match the strength of a neodymium magnet, and there's not much extra space to go around inside an electric motor. We know that Tesla can make some of this back by increasing efficiency. They've done that in the past. Just in the time between Model 3 and Model Y, the engineers were able to reduce the amount of rare earth material required for the electric motor without sacrificing any power. But inevitably, by switching over to a ferrite magnet, Tesla will lose some performance in their next-gen vehicle. So now, instead of going 0 to 60 in 6 seconds, it might take 8 or 9 seconds. Is that the end of the world? Absolutely not. This is a vehicle made for mass transportation, not the racetrack. Going all the way back to Nikola Tesla, Good inventors are simply trying to extract more functionality from the world around them. How can we do more work with less energy? How do we combine different principles to create something new and more effective? And that is what Tesla, the company, has continued to do throughout the past 2 decades.